Welcome to next lecture. In the previous lecture, we discussed single phase half wave rectifier by using a diode as main device. Now, in this lecture, let us discuss single phase half wave phase controlled rectifier with SCR as a main device. Now here, I just drawn the circuit diagram. The title is single phase half wave phase controlled rectifier with the resistive load. In the previous lecture also we have discussed the similar circuit, but diode was main device. Now let us discuss with the SCR as a main device. Here also the rectifier circuit source voltage is pure sinusoidal, that is given as Vs is equal to Vm sin omega t, and the source voltage terminals A and B. Okay. And here the load side, the terminals are X and Y, and output voltage let us denote with a symbol V0. This is basically instantaneous value. The output current is represented with the I0. Now voltage across this thyristor or SCR is denoted with the symbol V suffix T. So here the source voltage waveform is plotted just for quick reference, okay, and the x-axis this is 0, and here this is pi, and this is 2 pi, and here it is 3 pi. Okay. Now in this particular circuit, if you recollect SCR property, what is that? Whenever anode to cathode voltage is positive, that means whenever the SCR is forward biased, the junction J2 will be in the reverse bias condition. Okay. Now in that situation, if we supply suitable gate current, now in this particular case, who will supply that gate current to SCR? A gate drive circuit which is connected between gate and cathode will supply suitable gate current. What do you mean by suitable gate current? We discussed that SCR requires external gate current help until the regenerative process establishes within the two transistor arrangement. Once that process was establishes, we can remove the gate current. With that aspect, we told that SCR was also treated as latching device. Okay. Now if we supply this type of source voltage to SCR or this circuit, we can say that 0 to pi the device is forward biased. Okay. That means the SCR will wait for gate current pulse. Now that gate current pulse is given between 0 and pi. The instant where gate current is given is called a firing angle. Okay, is denoted with the symbol alpha. Now in the next cycle, the device is forward biased between 2 pi and 3 pi. Therefore the SCR is given with a firing angle yet an instant 2 pi plus alpha. Okay. So one more point here, basic point, follow carefully. You may have a question, why don't we trigger at some other instant? Why exactly at 2 pi plus alpha? The reason is, for example, whenever we are dealing with the gate drive circuits, during the design of the gate drive circuit, the pulses in practice, in practical circuits, will be produced on a time scale. Just degree or radian is for our convenience. Okay. For example, let us say source voltage is 50 Hertz. In that case, what is one cycle time? 1 by 50, 20 millisecond. So up to pi it is 10 millisecond. Up to pi by 2 it is 5 millisecond. At pi by 4 it is 2.5 millisecond. For example, the requirement is we need to trigger SCR at omega t is equal to pi by 4. In such cases, external gate drive circuit will be designed in such a way that once the source voltage has positive zero crossing, okay, in the gate drive circuit there will be a mechanism in order to detect this positive zero crossing of the source voltage. Once that positive zero crossing of source voltage is detected, from that instant, after 2.5 millisecond, a gate drive circuit will give a small gate pulse to SCR. That means from this instant, after 2.5 millisecond, if the gate drive circuit supplies a small gate current pulse to SCR, that is equivalent of SCR is triggered at omega t is equal to pi by 4. Now again in this source voltage pattern, when the next positive zero crossing of source voltage is occurred, that is at 2 pi. So from this instant, after 2.5 millisecond, where it is, that is at 2 pi plus alpha. Okay, so in this way the gate current will produce gate current pulses, gate drive circuit will produce gate current pulses periodically, that is equivalent of alpha in the first cycle, 2 pi plus alpha in the second cycle, and the next cycle 4 pi plus alpha, and so on. Now by using this gate triggering sequence, this type of sequence is called symmetric triggering sequence. By using this sequence, now let us draw various waveforms, V0, I0, output voltage and output current, and voltage across SCR or thyristor. So from 0 to alpha, what is SCR condition? SCR is in forward blocking state. SCR is forward biased, but it is not yet started conduction. It is waiting for gate current, that is due to reverse bias junction J2 in the SCR construction. So in the forward blocking state, what the SCR function? It will block the positive value of the source voltage. Therefore 0 to alpha, whatever the source voltage is, that will appear across the SCR. Okay, and once the SCR is triggered, voltage drop across the device, we assumed it is to be 0. So SCR voltage will be 0. Then what will happen? So up to alpha, as SCR is in the blocking state, you can replace SCR with the open switch. Hence no current will flow through the circuit and there is no output voltage also. Therefore from 0 to alpha, I0 is 0 and V0 is also 0. Now at omega t is equal to alpha, what is the source voltage magnitude? So what is the Vs equation? Vm sin omega t. If you substitute omega t is equal to alpha, then source voltage value is Vm sin alpha. That is the voltage applied across the load terminals. So once SCR is turned on, as voltage drop across the device is 0, you can say that load terminal X will be connected to source terminal A. Therefore voltage across XY terminals will be same as that of AB terminals. Okay, so from alpha to pi, what is output voltage? That is same as source voltage, right? So now if you look into the source voltage pattern, at alpha, that is Vm sin alpha, and at pi by 2, this source voltage will reaches to peak value and then it will come down. Okay, so output voltage at pi by 2, at pi by 2, that is a Vm, which is same as that of peak value of the source voltage, that is Vm. Okay, after then it comes down. The waveform shape should be exactly like this, right? Now, as the load is resistive, now if you write down here, when SCR is on, the basic circuit equation, how can you write? R multiplied with I naught is equal to Vm sin omega t. Therefore, it will give you Vm by R sin omega t. Vm by R sin omega t. Follow carefully here, with the diode and the resistive load also we have same equation. In that case, what was the conclusion? We told that the current flowing through resistor has the same waveform shape as of voltage across resistor. Now at this stage we can have one conclusion. Try to memorize this conclusion. Whenever we are dealing with the resistive circuits, okay, so voltage across the resistor and current flowing through the resistor, both will have exactly the same waveform shape. The only difference will be their peak values are different. Okay, therefore with this explanation, if you draw output current waveform, we will get output current waveform will be something like this. Okay, so what is the difference in this waveform? This waveform peak value is Vm by R. This waveform peak value is a Vm by R, whereas output voltage peak value was Vm. But both will have peak values at same instants, that is pi by 2. Both the waveforms will attain peak values at same instant. Now at omega t is equal to pi, follow carefully here, current flowing through the load is 0. The same I naught is flowing through thyristor also. The same I naught is flowing through thyristor also. Therefore we can say at this instant anode current has 0 crossing. Now if you recollect SCR theory, what are the conditions for SCR to be treated as turn off? The device should have, means anode current should have 0 crossing. Strictly speaking, it should be less than holding current. And then the device should be reverse biased. Now in this particular circuit, who is providing that reverse voltage for SCR? That is obviously source voltage. So you can observe carefully here, whatever the negative half cycle of the source voltage is there, that will provide reverse bias for the SCR. Therefore, from pi onwards, SCR will be treated as turn off switch until the device is triggered again whenever the device is a forward bias. Therefore, pi 2, from pi onwards, the device triggers again in the next cycle, that is at 2 pi plus alpha. SCR is replaced with the open switch. Current flowing through that open circuit is 0. Therefore, there is no current and no voltage also, because R into I naught is a 0. So then what happens? SCR is in the blocking state. Voltage across the thyristor is simply same as that of source voltage. So from pi to 2 pi plus alpha, this output voltage will be same as that of the source voltage. This entire half cycle will appear across the device. So what is the magnitude of this voltage at alpha? That is Vm sin alpha. At 2 pi plus alpha also the same thing. At 2 pi plus alpha, again the device is triggered, hence voltage drop across the device reaches to 0. Okay, voltage drop across the device reaches to 0. Now what is output voltage? From 2 pi plus alpha, again output voltage will be same as the source voltage. it will follows as in the first cycle. Okay, this is what V naught and I naught waveforms, and they will repeat periodically. If you notice carefully, what is the difference from diode circuit and these waveforms? Whereas in the diode circuit, these waveforms started from 0, now it is started after alpha. Okay. Now, in this waveform, what are the important things? How much time SCR was in conduction? SCR was in conduction from alpha to pi. Okay, that is one observation. Load current has peak value at pi by 2. Next, what is the maximum voltage that appears across SCR during its reverse bias condition? That is minus Vm. Hence, peak inverse voltage rating is equal to Vm. Okay. Next, another important point when we are dealing with the thyristors, now onwards, you just remember this. Whenever we plot voltage across SCR waveform, we should calculate two parameters. One is peak inverse voltage, second one is circuit turn off time. Now, if you recollect from thyristor characteristics, what was the definition for circuit turn off time? The time measured from the instant where anode current of SCR is 0. Okay, that is at pi, to the instant where reverse voltage due to external power circuit is 0. That is at 2 pi here. Okay, observe carefully. Circuit turn off time is measured from pi to 2 pi. Circuit turn off time is measured from pi to 2 pi. Now you may have a question. Sir, SCR is not in conduction from 2 pi to 2 pi plus alpha also. True, but 2 pi to 2 pi plus alpha is in forward blocking state. Forward blocking state should not be taken into account of circuit turn off time. That is the basic concept. Okay. Now, one more point. Now, in this particular rectifier circuits, the reverse bias condition, in other words, the favoring conditions for commutation of a thyristor are providing due to the natural property of the source voltage. Therefore, phase controlled rectifier circuits, the scheme of commutation is referred as natural commutation. It is also known as line commutation. Phase controlled rectifier circuits can also considered as line commutated thyristor based converter circuits. Okay, there is one more circuit which is having this line commutation concept. Step by step, once we are discussing different circuits, you will understand all of those aspects. Okay, so this is about various waveforms for the given circuit. Now let us write down few conclusions based on this waveform. Now just look at the waveforms and let us write down the conclusions. First point is conduction angle of SCR. From where to where SCR is in conduction? That is from alpha to pi. Therefore, that duration mathematically expressed as pi minus alpha. Okay. Next, output current is peak at omega t is equal to pi by 2. Okay, output current is peak value at omega t is equal to pi by 2. Next, peak inverse voltage is equal to Vm. Okay, peak inverse voltage is equal to Vm. Next, let us write down circuit turn off time. Circuit turn off time, omega tc, right? Omega tc. In the waveforms, we concluded that is from pi to 2 pi. Therefore, that duration is pi. In other words, tc is equal to pi by omega in second. circuit turn off time, Tc is equal to pi by omega in second. Okay, next. So these are the conclusions. One more point what we discussed, scheme of commutation is line or natural commutation. Okay, scheme of commutation is line or natural commutation. Now let us find average output voltage. 1 by periodicity first, 1 by 2 pi. The integration limits are from alpha to pi. Alpha to pi. What is the equation for the function? That is Vm sin omega t. Okay. So now let us simplify this integration. Vm divided by 2 pi, integration for sin omega t is minus cos omega t. Limits are from alpha to pi. So this can be simplified as Vm divided by 2 pi multiplied with upper limit minus cos pi is equal to 1, minus of minus plus cos alpha. This is the expression for average output voltage. Okay, next. How can you write average output current? That is V naught by R, where V naught is a average output voltage. Okay, next. Now here load is a resistive load. We should calculate output power in terms of RMS voltage. Therefore, first let us find out the expression for RMS voltage. How to find? VOR square is equal to 1 by periodicity 1 by 2 pi. Integration limits are from alpha to pi. Vm square sin square omega t d omega t. Okay. Now let us simplify this. Vm square divided by 2 pi, limits from alpha to pi, sin square omega t 1 minus cos 2 omega t divided by 2. Integration is with respect to omega t. Okay. Next, Vm square divided by 4 pi, where integration for 1 is omega t minus sin 2 omega t divided by 2. The limits are from alpha to pi. Okay. Next, Vm square divided by 4 pi. Substitute the limits, upper limit minus lower limit. What you will get? Pi minus alpha minus half into upper limit sin 2 pi is equal to 0. Leave that. Lower limit minus of minus. So I can make this minus to be plus first, into sin 2 alpha. Okay. This is about VOR square. But from this, how can you write RMS voltage? Take root of this value totally. Therefore, we will get Vm here, denominator 2 root pi multiplied with pi minus alpha plus half sin 2 alpha under root. This is the expression for RMS output voltage. Okay, this is the expression for RMS value of the output voltage. After this, now we can write down output power. VOR square divided by R, right? So if you substitute this value, what we will get? Where VOR square is equal to VM square divided by 4 pi R multiplied with pi minus alpha plus half sine 2 alpha. This is the expression for output power. Okay. Next. Now I would like to write RMS value of output current is equal to RMS value of the output voltage divided by resistance. Okay. Now if you look into the circuit diagram, because of this simple series circuit in the half-wave rectifier circuit, I0 and IS both are same. Therefore, RMS value of the output current you can also represent as RMS value of the source current. RMS value of the source current. Okay. So this is the expressions for output power, RMS output current and RMS value of the output voltage. Now let us define another important parameter, that is input power factor. It can be defined as IPF is equal to power delivered to the load divided by Vs multiplied with Is. Now as the load is resistive, P0 can be written as VOR square divided by R. Denominator Vs multiplied with, in place of Is, what we can write? VOR by R. Okay. So R can be cancelled, one VOR can be cancelled. Therefore, what is the input power factor expression? RMS output voltage upon RMS value of the source voltage. Now, if you divide RMS value of the output voltage with the source voltage, where source voltage is Vm by root 2, then what you will get? Okay, let me write down here. Vm by 2 root pi into pi minus alpha plus half sine 2 alpha under root, right? Divided by, this is RMS output voltage, divided by source voltage RMS value, that is Vm by root 2. Then you can cancel Vm and Vm, right? Now this IPF can be expressed as 1 by under root 2 pi, okay, this root and this 2. So 1 by under root 2 pi multiplied with pi minus alpha plus half sine 2 alpha under root, okay, half sine 2 alpha under root. So this will give you expression for input power factor. Okay. Now from this expression I want you to find one conclusion. What is that? Suppose if firing angle increases, then what will happen to input power factor? Suppose if alpha increases, sine 2 alpha term will increase, no doubt about it. But pi minus alpha term will decrease. But in the single expression, one term increases, another term decreases. Maybe you may not have a proper justification by using this equation. So in order to get proper justification, let us look into the waveform. Let us look into the waveform. Now see this waveform. If alpha increases, what will happen? This waveform will reduces, isn't it? When this waveform got shrink, what happens to RMS voltage? RMS voltage will also reduces. In other words, power delivered to the load will reduce when alpha increases. When power delivered to the load decreases, input power factor, numerator is decreasing, Therefore, input power factor will obviously reduces. So, what is the final conclusion here? If alpha increases, as a P naught decreases, I can write here input power factor will decreases. Okay. If you remember in the introduction lecture, I mentioned one statement at the time we have not justified mathematically. Okay. In PCR circuits, when alpha increases, input power factor will decrease. This is the basic drawback. This is the basic drawback. Okay. So what this drawback is very important. Why? Because for PCR, phase controlled rectifier circuits, the input is power system grid, isn't it? Therefore, if at all this phase controlled rectifier circuit is placed in a power system grid, the input power factor will deteriorate. There are certain methods for improvement of this power factor which are not in the syllabus. But with this explanation, we will highlight that there is a problem with the power factor input side whenever you are using phase controlled rectifier circuits. Now, let us take one example. In the given circuit, a thyristor converter is feeding a resistor R. The power consumed by R in the absence of SCR is P. In the presence of SCR, the power consumed by SCR by R at alpha is equal to 90 degree would be reduced by a factor of. Okay. Now let us see this problem. In the absence of SCR, means resistor is directly connected to source voltage without the device. Okay. In that condition, the power is given as symbol P. So what is that power expression? RMS voltage square divided by R, isn't it? That means you have to write source voltage RMS value directly. Why? Because the resistor is directly connected to source voltage without that SCR. Okay. Now from the source voltage specification, you can say capital V is RMS value. Therefore, V square upon R, that is P expression. Now in the presence of SCR, so in the presence of SCR means the resistor is connected to sinusoidal source through SCR. So under that condition, what is the expression for power? Okay, let me use a symbol P1 here. So Vm square upon 4 pi R multiplied with pi minus alpha plus half sine 2 alpha. Okay, pi minus alpha plus half sine 2 alpha. But what is the given condition? P1 when alpha is equal to 90 degree. In other words, P1 when alpha is equal to pi by 2. So what is this value? Vm. What is Vm here? Root 2 multiplied with V whole square divided by 4 pi into R multiplied with pi minus pi by 2, that is simply pi by 2 plus half into sine 2 into pi by 2, that is sine pi is 0, hence it is 0. Now I can cancel this pi and pi here, then this 2 and 2 will cancel out, then what is the value here? Vm square by 4 into R. So what is the final takeaway for this question? P1 with alpha is equal to pi by 2 is 1 by 4 times P. What is P? when the SCR, when resistor is directly connected to sinusoidal source without SCR, so would be reduced by a factor of, so P1 with alpha is equal to pi by 2 will reduce by a factor of 1 by 4 by reduced by a factor of 1 by 4. The same question we can also write, it reduce by 4 times, okay, like that also we can interpret. So this is the final answer. Now let us take one example. Consider a phase controlled converter shown in the figure. The thyristor is fired at an angle alpha in every positive half cycle of the input voltage. If the peak value of the instantaneous output voltage equals 230 volt, the firing angle alpha is close to. Now here, even though this is a simple objective question, let us draw output waveforms for the given firing angles 40, 90, 135 and 180 degree. So from the given source voltage, the first point is the peak value of the source voltage is 230 multiplied with root 2 volt. Okay. So when the source voltage peak is 230 root 2, what is the angle where the source voltage is equal to 230 volt? That angle will be 45 degree and 135 degree. Okay, 45 and 135 degree. Now, for example, if alpha is equal to 45 degree, if alpha is equal to 45 degree, what will be the output voltage? V0 waveform will start from 230 volt. Okay, yet 90 degree output voltage will increases to 230 multiplied with root 2 volt. 230 multiplied with root 2 volt. So similarly in the next cycle, again the V0 waveform will be same as in the first cycle. So what do you mean by that? In the V0 waveform, you can identify that the peak instantaneous output voltage is 230 into root 2 volt. Therefore, alpha 45 degree is not suitable for the given question. Now, if alpha is equal to 90 degree, in this case, V0 waveform will start from 90. Okay, V0 waveform will start from 90 with a magnitude of 230 into root 2. This is V0 waveform for alpha is equal to 90 degree. After this 90 degree, V0 waveform will reduce and reaches to 0. Similarly, in the next cycle, output voltage will start at this instant with a peak value of 230 into root 2. So what is the peak instantaneous output voltage in this waveform? Again 230 root 2. Hence, not correct answer. Okay. Now, if we draw V0 waveform for alpha is equal to 135 degree. Okay. So in this case, V0 will start from 230 volt. V0 will start from 230 volt. After then it will decrease. Similarly, in the next cycle, V0 will start from 230 and will decrease. Okay. So in this particular case, the peak instantaneous output voltage is 230 volt when alpha is equal to 135 degree. Therefore, this is the required answer. Alpha is equal to 135 degree is a required answer. With that we got what is the required answer, but if you plot output voltage waveform for alpha is equal to 180 degree, you will notice one important conclusion. What is that? When alpha is equal to 180 degree, thyristor will not start conduction at all. Therefore, output voltage waveform is 0 in the entire cycle. So, with this waveform, we can have one important conclusion. What is that? In the single phase half wave uncontrolled rectifier, when the load is resistive, the control range for alpha is 0 degree less than alpha less than 180 degree. So, if firing angle is in between 0 to 180 degree, then only output voltage can be controlled. Now, the next case is inductive load, single phase half wave PCR. Full form of PCR is phase controlled rectifier. Okay. So, the load is inductive, that is RL nature. Just like other circuits in the sense other rectifier circuits, source voltage is pure sinusoidal, and here the device is SCR. If you recollect from the previous lecture, RL load sinusoidal source with a diode we already discussed. Now, what are the differences with respect to SCR? That's we'll try to understand. Here, voltage across SCR is represented with the VT, and output current is denoted with the symbol I0. Output voltage will be measured across the terminals X and Y. Source terminals are A and B. Okay. Now, with this, let us start drawing the waveforms. As a SCR is a main device here, from 0 to pi, as the source voltage is positive, device will be forward biased and is in forward blocking state. Therefore, it will wait for gate current pulse. So, that gate current pulse will be supplied by the external gate drive circuit at an angle alpha. Okay. So, in the next cycle, again the device will be triggered at 2 pi plus alpha, right? Now, let us draw output voltage, output current, this is I0, and voltage across SCR. From 0 to alpha, SCR will be in forward blocking state. Therefore, it will block the positive value of source voltage. Yet omega t is equal to alpha, as the device is triggered with respect to gate current pulse, voltage across SCR will be 0, and at this instant the source voltage will be Pm sin alpha. Now, from alpha to pi, output voltage will be same as the source voltage. Okay. Yet omega t is equal to alpha. What is the source voltage? Vm sin alpha. That will appear across the load. What is the reason for that? Once SCR is turned on, voltage drop across the device will be 0. Therefore, load terminals XY will be connected across the source terminal. Now, in this particular circuit, just like a previous one, output voltage means it is measured across the terminals X and Y. Now, in order to draw output current, we should look into the equation for output current. Let us see that. Suppose when SCR is turned on, I can write down the basic circuit equation as when SCR is on. What is the basic circuit equation? R into I naught plus L into d I naught by dt is equal to source voltage, that is Vm sin omega t. Now, if you recollect from our previous lecture, this first order differential equation we have already solved it. Now we will use that solution here. What is that? I naught is equal to Vm divided by root of R square plus omega L whole square multiplied with sin of omega t minus phi plus k into e power minus RT by L, right? So this was the original solution. After this, we calculated k value by applying initial condition, okay? So in this particular case, what is the initial condition? So I naught is equal to 0 yet the instant when the device is turned on, okay? This is what initial condition, where the device is turned on, that is at omega t is equal to alpha. Therefore, let us substitute that initial condition. Left hand side I can equate to 0, right hand side we can write Vm divided by square root of R square plus omega L whole square multiplied with sin alpha minus phi. I am substituting omega t is equal to alpha here, plus k into e power R by L multiplied with, when omega t is equal to alpha means t is equal to alpha by omega, okay? T is equal to alpha by omega. Now, by using this, how can we write k value? Minus Vm divided by square root of R square minus, R square plus omega L whole square into sin of alpha minus phi. This term is to be multiplied with e power R alpha divided by omega L, okay? You have to multiply with this number. Now, what we can do, substitute k value into I naught equation. Substitute k value into I naught equation. Then what we will get? I naught is equal to Vm divided by square root of R square plus omega L whole square multiplied with sin of omega t minus phi. Now let me write down k value plus, now open a bracket, minus Vm divided by square root of R square plus omega L whole square into sin of alpha minus phi multiplied with e power R alpha by omega L multiplied with e power minus RT by L. Now, this can be rearranged as, I would like to take Vm by root of R square plus omega L whole square term common. Then what we can write here, multiplied with sine of omega t minus phi minus sine of alpha minus phi. Now I would like to combine these two terms as e power minus r by omega L multiplied with omega t minus alpha. Okay, so this is the equation for output current. In this equation, what is the value of phi? Tan inverse omega L divided by R. Okay, this is what the expression for the output current flowing through the circuit. Now observe carefully here, compare this equation with respect to our earlier diode and RL circuit. There also we had a same equation with the slight differences. What are the differences? SCR and diode, these two devices are different in terms of starting condition. Diode can start from omega t is equal to 0 itself, whereas SCR will start from omega t is equal to alpha. Okay, so if you substitute alpha is equal to 0 in this equation, you will get back whatever equation we derived in the diode case. In the diode, here we had plus sine phi. You just cross verify with the previous lecture. If you substitute alpha is equal to 0, you will get that plus sine phi. If you substitute alpha is equal to 0, here you will have e power minus RT by L. That's what we had in the diode circuit. So what do you mean by that? In the previous diode circuit and RL load, we told that output current has two major components. One is sinusoidal component and the other is exponentially decaying component. Okay, so in this case again output current has those two components. What is the only difference here? The starting point is different. In case of diode, the current started from 0. In case of SCR and RL load, the same sinusoidal and exponentially decaying component will start from alpha. So with this explanation, if we draw the combination of sinusoidal and exponentially decaying component, we will get the output current waveform something like this. Okay, what is the difference from diode analysis? The starting point. In case of diode, this current started from 0, now it started from alpha, and this current reaches to 0 at omega t is equal to beta. Okay, so what is the point here? Load current is flowing from alpha to beta. In this circuit, the only path is through SCR. Okay, therefore as long as the load current is flowing, SCR will be in conduction. Until SCR is in conduction, load terminals X, XY will be connected to source terminals AB. Therefore up to beta, the output voltage will be same as that of source voltage. So if you look into up to beta, the negative portion of source voltage will appear across the load side. This is what output voltage waveform. Every step by step you just compare what is the differences we are getting from the previous analysis and moving forward, right? Now as this current is 0 at beta, SCR can be turned off through natural commutation process. Up to next instant device is triggered, till that instant as the device is in the off state, you can say that output current and output voltages are 0. Then what will happen to SCR? The entire source voltage, that is from beta to 2 pi plus alpha, this source voltage now will appear across SCR. Therefore, at omega t is equal to beta, this point, source voltage has negative magnitude. Okay. So, what is this magnitude here? That is Vm sin beta. What is that magnitude? That is Vm sin beta. Generally here one possible mistake is people will write minus Vm sin beta. Okay, you need not to write a minus here because beta is generally greater than pi. Sin of greater than pi is obviously negative. No need to write minus separately. If you write minus separately and substitute beta value, for example 200 degree, you will get the magnitude as positive. It is wrong. Now from beta to 2 pi plus alpha, I need to draw the waveform shape of source voltage. I need to draw the waveform shape of the source voltage. In this way, our source voltage that will appear across the SCR. Yet omega t is equal to 2 pi plus alpha, as the device is triggered again, voltage drop across the device will be 0. Okay, next. Now from this instant again the same V0 and I0 waveforms will be repeated in the next cycle. This is how V0 and I0 waveforms. Okay, so this is what V0 and I0 waveforms. Now one important point here is the conduction angle for SCR is measured from alpha to beta. Okay, conduction angle for SCR is measured from alpha to beta. Next, circuit turn off time from where to where? From the instant where SCR current is 0, that is beta, to the instant where reverse voltage due to external circuit is 0, that is at 2 pi. So beta to 2 pi will give you circuit turn off time in this particular case. And when the device is in the reverse bias condition, this is the maximum voltage, that is minus Vm. Therefore, we will get peak inverse voltage is equal to Vm. Okay. So these are some of the important conclusions. Now let us write down those conclusions one by one. First one is conduction angle of SCR. That is from alpha to beta device is in conduction, hence the duration can be beta minus alpha. Next one, circuit turn off time omega tc is equal to, that is from beta to 2 pi interval. Therefore, we can write it like this, 2 pi minus beta. In other words, Tc is equal to 2 pi minus beta divided by omega in second. Okay, 2 pi minus beta divided by omega in second. Next one is peak inverse voltage, that is equal to Vm. So while writing PIV, you need not use minus symbol explicitly. Next, voltage across SCR at the time of turn off. Voltage across SCR at the time of turn off. I can write it like this, Vt at omega t is equal to beta. What is that value? That is Vm sin beta. Okay, Vm sin beta. Next, let us write the expression for average output voltage. What is that? 1 by periodicity, integration limits alpha to beta, Vm sin omega t, integration is with respect to x-axis. I told this point in the previous topics. Therefore, Vm by 2 pi, what is integration for sin omega t minus cos omega t, limits from alpha to beta. Okay, Therefore, this will give you V naught is equal to Vm by 2 pi into upper limit minus cos beta. Lower limit is minus of minus, that is plus cos alpha. Okay. This is the expression for average output voltage. After this, we can write average output current is equal to V naught by R. Average output current is equal to V naught by R. Now, just like in our previous circuit, diode circuit, we told that how to find beta. Here also the same concept. To find beta, what we need to do? Equate I naught with 0 at omega t is equal to beta. Okay. Here we have I naught equation readily. Therefore, if I substitute in that, we will get sine of beta minus phi minus sine of alpha minus phi into e power minus r by omega L multiplied with beta minus alpha is equal to 0. Okay. This is one non-linear equation. These type of equations can be solved by numerical methods. Can be solved by numerical methods. Now, let us consider another case. From our earlier RL load, I just removed that resistance part. Okay. Now, let us see what is the analysis here. Now, let us take this as an example problem. For example, if alpha is equal to 30 degree, then find what is gamma value for the thyristor, what is beta value for load current. Okay. Let us take by using this firing angle, let us draw output voltage and output current waveforms. So, as alpha is given 30 degree, SCR will start conduction from 30 degree, isn't it? Therefore, the first step what I can say, 30 degree to 180 degree, pure inductor will be connected to sinusoidal source. Therefore, how much time the inductor voltage is positive? That is for a duration of 150 degree. Therefore, from 30 degree to 180 degree, load current will increases. We'll see what is the equation for that. So, if you recollect from our earlier pure inductor and a sinusoidal combination through a diode, what we discussed, how much time inductor will store energy, it will take same time to release that energy. When there is no dissipating element like a resistor, it will send back that energy to source itself, right? Therefore, how much time this inductor stores energy? For a period of 150 degree. Okay. Therefore, it will release energy in another 150 degree. So, it started at 30 degree and hence it will release energy in another 150 degree means, now you can say where it will reaches to 0 degree. It will be 330 degree. Therefore, this current will reduces to 0 at 330 degree. So, from 30 to 330, as the current is flowing, that current has to flow through SCR only, no other path in the circuit. Therefore, until the device is in conduction, inductor will be connected to the source. Hence, from 180 to 330, whatever the negative half cycle of the source voltage, that will appear across the load. In this way, you can also justify that volt second balance concept. Load is pure inductor. Positive area is equal to negative area, and hence volt second balance will satisfy. Now, again at 2 pi plus alpha, that is 390 degree, the same waveform will repeat periodically. This is how the V0 and I0 waveforms. Now from this waveform, you can easily understand, or you can easily answer it. What is conduction angle for thyristor? I can say 300 degree. Where the load current extinguishes, beta is equal to 330 degree. Therefore, what are the answers for this particular question? Gamma t is equal to 300 degree, beta is equal to 330 degree, right? Now, for example, without drawing the waveform, if I give you alpha is equal to 60 degree, then what is your answer for gamma t? Try. So, alpha is equal to 60 degree means from where to where inductor will store energy? 60 to 180. So, how much time it is? 120 degree. So, how much time it requires energy to release? Another 120 degree. Therefore, conduction angle will be 240 degree. And what could be beta? So, it started a delay of 60 degree. Therefore, it will release that energy with a 60 degree early. Therefore, beta will be 300 degree. Now, if I don't give you these numbers, I want you to generalize this discussion. Okay. In that case, how can you express beta? Beta is equal to, now first identify how much time inductor stores energy for a period of pi minus alpha. It requires another pi minus alpha to release that energy. Therefore, this is what this is the conduction angle, gamma t. Okay, gamma t. So it stores energy for a period of pi minus alpha, and it will release energy for a period of another pi minus alpha. Therefore, total conduction will be 2 times of pi minus alpha. Now, what could be beta? I can write it like this: 2 pi minus alpha. It started with a delay of alpha, so the energy will release before 2 pi. So that is a 2 pi minus alpha. The next question is, I want the expression for I0. I want to find the expression for I0. Now that means equation for this particular function, equation for this particular waveform. Okay. So how can I write? When SCR is on, when SCR is turned on, I can write here L into d I0 by dt is equal to Vm sin omega t, right? So in our diode circuit, we solved this equation. What was the result? Vm by omega L multiplied with minus cos omega t plus k. This was the original solution. How can you find the k value? By using initial condition. Okay, by using initial condition. Now in this particular circuit, can you tell me how can you express the initial condition? That is, I0 is equal to 0 at omega t is equal to alpha. Okay, therefore left hand side we can make it 0, right hand side Vm by omega L multiplied with minus cos alpha plus k. Therefore, it will give you K is equal to Vm by omega L into cos alpha, isn't it? Now, the final expression for output current will be Vm by omega L multiplied with cos alpha minus cos omega t. This is the final equation. Now, if you try to cross check with respect to diode, in case of diode, what was the result we have? Diode means alpha is equal to 0. Therefore, in case of diode, we already got it. Vm by omega L multiplied with 1 minus cos omega t. This is the analysis of pure inductive load. One more point here. In the waveform, if you observe carefully, at what instant this I0 has peak value? I0 has a peak value at omega t is equal to pi. That conclusion is same as in diode also. Therefore, if you want, you can write down here I0 is peak at omega t is equal to pi. What was average output voltage because of load is pure inductor? According to volt second balance concept, average output voltage will be 0. Now, let us take one numerical example. A 230 volt 50 hertz 1 pulse SCR controlled converter is triggering at a firing angle of 40 degree and the load current extinguishes at 210 degree. Find the average output voltage, current and circuit turn off time for a load of R is equal to 5 ohm and L is equal to 2 millihenry. Now, let us look into the solution. Here what is mentioned? Single phase 1 pulse SCR controlled rectifier. Alpha and beta values are given. We need to calculate average output voltage. So, first let us write down the expression. Vm by 2 pi multiplied with cos alpha minus cos beta. Okay. Therefore, what is Vm here? 230 multiplied with root 2 divided by 2 pi. Okay. Into cos 40 degree minus cos 210 degree. Okay. Minus cos 210 degree. This numerical value I calculated and I got 84.49 volt. This is the first one, average output voltage. Next, average output current I0 is equal to V0 by R. What is V0 here? 84.49 divided by the load resistance is 5 ohm. This value is 16.9 ampere. Okay. Next. Third question is circuit turn off time. So what is the expression for circuit turn off time? 2 pi minus beta divided by omega. So how to substitute the numericals? 2 pi minus, you have to substitute beta in radian. Why? Because 2 pi is in radian. So that is 210 multiplied with pi by 180. Okay. Denominator omega is nothing but 100 pi. So this value I calculate and I got an answer 8.33 millisecond. Let us take another numerical example. An RL load is energized from single phase 230 volt 50 hertz source through a single thyristor, has R is equal to 10 ohm and L is equal to 0.08 Henry. If thyristor is triggered in every positive half cycle at alpha is equal to 75 degree. Find the expression for current as a function of time. Now let us look into the solution. In this problem, it is asked that find the expression for I naught as a function of time. So just from previous theory, if you write down the equation for current, SCR, sinusoidal source and RL load, what is the equation? Vm divided by square root of R square plus omega L whole square multiplied with sine of omega t minus phi minus sine of alpha minus phi into e power minus r by omega L into omega t minus alpha. Okay. So let us calculate each term one by one. Okay. So first let us find phi value. What is the expression for phi? Tan inverse omega L divided by R. So that is tan inverse, as the frequency is 50 Hertz, omega means 100 pi, L value is given as 0.08 divided by resistance value is 100. I calculated this value and this is 68.3 degree. This is the value I got. Okay. So one value I got it. Next. Now let us find out Vm divided by under root R square plus omega L whole square. So what is this value? Vm is 230 multiplied with root 2. Denominator square root of, where R is 10 square plus omega L whole square. What is that? 100 pi into 0.08 whole square. Okay. This value I got it around 12.025 ampere. Okay. This is the value of that term Vm by root of R square plus omega L whole square. Now observe this equation carefully here. The second term I can write it like this: Vm divided by root of R square plus omega L whole square multiplied with sine of alpha minus phi. If you recollect from the derivation, this is what the term we have, multiplied with e power r alpha, okay, e power r alpha divided by omega L, okay, e power r alpha divided by omega L. Now here what is this value? Vm is 230 into root 2 divided by, anyhow we had this value, divided by r square plus omega L whole square, 10 square plus 100 pi multiplied with 0.08 whole square. Okay, this is the first term, into sine of, what is alpha here? 75 minus phi value 68.3 into e power r value. What is r value? That is 10 into alpha is 75. It is in degree, you have to convert into radian. So multiply with pi by 180 denominator is omega L, that is 100 pi into 0.08. This total value is 2.36. Okay, 2.36. Now we got all of the values, and one more thing here, if you separate out these two terms, I will have e power minus r by L into t. So what is r by L? R is 10 divided by L is 0.08. This value is 125. Therefore, now you can write the solution or expression for output current as a function of time. How can you write? First, 12.025 multiplied with sine of omega t. Omega means 100 pi. 100 pi, I can write it simply 314t minus phi value we got 68.3 degree. Okay, minus what is this number we got? 2.36 into e power minus 125t. Okay, so this is what the expression for current in time domain. Okay, so this is what expression for current as a function of a time. Now let us take another numerical example. A diode circuit feeds an ideal inductor as shown in the figure. It is given that source voltage is 100 sine of omega t, where omega is equal to 100 pi. That means frequency is 50 hertz. And the load inductance is 31.83 millihenry. The initial value of inductor current is 0. Switch S is closed at 2.5 millisecond after positive zero crossing of the source voltage. The peak value of inductor current in the first cycle is. Now let us look into the solution. Here I just drawn the circuit diagram for quick reference. Source voltage is given, load is a pure inductor. This is very interesting problem, follow carefully. When the frequency is 50 hertz, first point should be in your mind is cycle time, means one sinusoidal cycle will complete in 20 millisecond, right? So switch is closed at 2.5 millisecond, that is equivalent of omega t is equal to pi by 4, isn't it? Now suppose if this switch is not there, we know diode will start conduction from omega t is equal to 0. But because of this switch, diode will start conduction from the instant where it is closed. That is equivalent of omega t is equal to pi by 4. So it is not mentioned in this circuit diagram, but I can treat this particular section as a thyristor. This particular section as a thyristor with alpha is equal to pi by 4. With alpha is equal to pi by 4. Why? Because suppose in this place if I have a thyristor and if I give alpha is equal to pi by 4, then what will happen? SCR will start conduction from the instant at 2.5 millisecond after positive zero crossing of source voltage. Okay. Therefore, this circuit we can treat it as a sinusoidal source, a thyristor and an inductor. So we can write down the expression for current small I naught is equal to Vm divided by omega L multiplied with cos alpha minus cos omega t, isn't it? So in this particular case where alpha is equal to pi by 4. Now follow problem carefully. Nowhere it is mentioned that thyristor is placed in the circuit, and it is not at all given firing angle in data. But The meaning is that only. Okay, the meaning is that only. Therefore, let us substitute. Now, one more point from SCR and pure inductor combination. In the waveforms, we had one more conclusion. I naught is peak at omega t is equal to pi, isn't it? I naught is peak at omega t is equal to pi. Therefore, IOP means you have to calculate this expression with alpha is equal to pi by 4 and omega t is equal to pi. Now substitute the values. If you want, I can write down here IOP, that is at omega t is equal to pi. So what is Vm here? That is 100 divided by omega is 100 pi, inductance value is 31.83 millihenry. Therefore 10 power 3 I can write it in the numerator. Cos alpha, cos pi by 4 is 1 by root 2 minus cos pi, that is plus 1. This numerical value is 17.07 ampere. Okay, this is the answer. Now with this we can conclude this lecture, and different loads we'll see in the next lecture. Thank you.